Hey everyone, in this video we're going to be talking about something really cool called slope fields, and they're basically a way that we can illustrate what possible solutions to a differential equation will look like. So if we have a differential equation in this form, now by now we should be used to this form, recall that our differential equation can be a function of x and y. So therefore, if we plug in a specific value for x and a specific value for y, we should get a specific value for dy dx. Now again, let's think back to last semester when we talked about derivatives. What does dy dx represent? Well, it represents the slope of a line tangent to the curve. That is the definition, or the graphical definition, of what a derivative is. So if we plug in a unique x and y coordinate, a differential equation can tell us what the slope of the solution would look like if the solution indeed passes through that x and y point. Now when I say solution, recall that if dy dx is our differential equation, that means our solution is going to be y equals something. Now, if we were given an initial condition with this differential equation, we could go through and actually solve the particular solution and know exactly what that curve looks like. Or one thing we could do is we could use that differential equation to draw out a slope field. Just basically say, okay, if the solution happens to pass through any of these x and y points, this is what its slope would look like at that particular point. Now it's important to note that a slope field will not, and I said this in bold and underlined, and in all caps, so it's got the trifecta there of when a teacher is trying to literally scream at you without screaming at you, telling you something is incredibly important that you have to remember. And this is the thing that I think a lot of students get confused with when they start doing slope fields, is that a slope field doesn't tell you exactly what the solution to the differential equation will be. It just says if the solution happens to pass through this point, this is what its slope looks like. However, these can be very useful because if we're given an initial condition, we can make up a slope field. And with an initial condition, that basically tells us a point that our solution will go through, and we can therefore use the slope field to get a general idea of the shape of our solution y to our differential equation. So let's start talking about them, and let's start actually looking at slope fields. Now, contrary to a lot of the other Desmos files in this class, I didn't make this one. I actually searched for this one online, and it's really cool because someone must have just made it because this wasn't even available a year ago. But this is what a slope field looks like, okay? So how do we make sense of this thing? Well, remember, I told you a slope field just tells you what the slope of a function is going to look like at a particular point. So in this case, they called it g, not f. It's still a differential equation. Our differential equation is xy. So what we should do right now is let's write a little table over here to this side. Let's look at x, let's look at y, and then let's look at slope. Remember, slope is dy dx, okay? So that is that function g of xy. So when x is 0 and y is 0, the slope will be x times y, or 0 times 0, which is 0. So let's look right here. The slope is 0 when x and y are equal to 0. A flat line is an indication of a 0 slope, okay? Now, what if we keep y 0 and we move x? Well, as we can see from our differential equation right here, if y stays 0, g is also going to be 0. So whenever y is 0, we get a 0 slope. And as you can see, as we move along the x-axis, which is where y equals 0, we always have a 0 slope. Likewise, if we plug in x equals 0 and move up the y-axis, we are also going to get a 0 slope every single time. So right now, we see the utility of a slope field. It's telling us what the slope of that function looks like if it passes through that point. Now let's say x is 1 and y is 1. Well, x times y is also going to be 1. And if we look at that point right there, we have a slope that looks roughly like a slope of 1. Now let's keep x equal to 1 and now make y 2. Now that makes the slope 2, and as you can see, when we look at the next point up, the slope is just a little bit steeper. That's because the slope of 2 is more steep than the slope of 1. So hopefully you get the idea at this point. If we wanted to go through and make a grid of all of these x and y points that are on here, what we would see is that these lines on this slope field just represent what the slope would be at that particular point. But again, the slope field doesn't tell us what the solution looks like. It just tells us if the solution goes through this point, this is what the slope is going to be. So let's visualize this slope field a little bit better by actually looking at a solution. Now, you guys know the method of separation of variables by now. If you want to, pause the video and apply it to this function right here. And if you do that, you'll eventually get a solution. Let me collapse this. Or actually, you'll eventually get a solution of this right here. And so don't worry about the h of x down here. We'll get to that later. But let me actually erase all the ink on this page. But you'll notice if I highlight this solution, check that out. Doesn't that solution look like it matches up with the slopes that were indicated by the slope field? Now in this case, I can set my value of c and I can change it a little bit. If I make c go up, it moves up through there. If I make c go down, it moves down. And it can go, and it can take on a number of different solutions. Now, some of you guys might be saying, well, what about all this stuff way to the left and way to the right? It doesn't look like the solution is passing through any of those points. Well, if I make my c smaller and smaller and smaller and smaller, you can see, doesn't it look like the slope of that function is matching up with the slope that was indicated by the slope fields? So again, if we're given a point that our function goes through, we can basically dictate what that slope field will be. So for instance, I can actually move, check this out, I can move the point of my slope field to focus on one point. And notice that the slope of this black line changes based on where I move it. I can either move it in the x direction or in the y direction. But let's say I move it, let's just go somewhere around here. Let's just look at that point. Let's pretend our function goes through that point, okay? How would we be able to visualize what this function looks like using the slope field? Well, when we're at this point, it's saying we have a super steep positive slope, okay? So therefore, a super steep positive slope looks something like that, okay? Now, as we go to the left, we get still super steep positive slopes, but notice as we move down in here, the slopes get less and less and less and less. So we can say, okay, we basically know that as we move, as we're ticking along going down the x-axis, our slope is going to get shallower and shallower. So it'll look something like that. And then we'll just have the opposite effect when we go up the other side on the y-axis. Now again, if we know it goes to that point, obviously I haven't drawn this one symmetrical. So that's not going to work because this is a symmetrical slope field, so it'd probably look a little bit more like that. Anyway, like I said, a slope field can be used to get a general shape of what the function looks like, but it's not the whole thing. And in reality, I was kind of trying to just illustrate what the slope was doing. But if we look at the slope field, really, if we look at this point and this point right here, I didn't draw the slope quite steep enough. I think this one would actually get even a little bit more of a kind of U-looking shape. There we go. That fits the slope field a little bit better. So if we go back and we highlight our solution, and let's move that C value out. So there we go. So there we go. Now when we look at the solution, it looks fairly similar to what we had before. And again, like I said, the first one where it wasn't so U-shaped, that was really just to illustrate how we can get a general solution. But if we really get exact with following those slopes, we can actually get something that's pretty close to the shape of what the actual solution will be. But again, it's kind of an eyeball approximation, so we can't treat it as gospel at this point. So let's look at a different differential equation here. Now we just went over a video. This equation should look kind of familiar to you. This is the solution to the logistic differential equation. So if we plug that equation in, k over m y times m minus y, so that gives us this type of slope field. And now if we highlight this solution, let's change our c value to be a little bit bigger. Okay, there we go. So that was a nice voice crack. Anyone pick that one up? With a microphone, it just comes through so crisply. So anyway, I already have these sliders up here. I can move my values back and forth, and it will change the differential equation. And wow, yeah, we went a little bit crazy with that. Let's get this back to something decent. Okay, there we go. So we can move these values back and forth, but notice that if I change, for instance, this C value, first of all, take a look at the green line. Doesn't that green line look like it follows all of those slopes that are in that slope field? But notice that we get kind of no action down in here or up in here. Now remember, a slope field just tells you what the slope will look like if it specifically passes through that point. Now it turns out this particular solution doesn't pass through those points, so therefore those slopes are irrelevant to this particular value of C. But if I change that value of C, if I go here, and then make a negative, now look, now we've actually engaged those slopes in here. Now, in all practical purposes, it doesn't really make sense to put a negative C value in the logistic differential equation because when we model population, no populations have a vertical asymptote in their population at some positive time like this one does. So it's a little bit ridiculous for a practical application. But again, you can see the slope field doesn't lie. It tells you what the slope will look like if the solution happens to pass through those points. Okay, so let's look at one example. This is similar to a type of AP problem you might be asked. So why don't you pause the video and just give this one a try. All right, if you've tried this one, one method you can do when you're starting to look at slope fields is grid everything out and actually put, x equals 0, y equals 0, x equals 1, y equals 1, and then go so on and so forth. That takes a little bit of a long time. You can actually figure out what slope fields will look like by using a couple tricks, and those tricks I like to use are determine where the slope is 0 and where the slope is infinite. So if we look at where the slope is 0, well, that's obviously going to happen when x is equal to 0. So anytime x is equal to 0, meaning we are along the y-axis, our slope is going to be 0. And as we can see, it's a little bit hard to tell from these, but if you zoom in, these slopes right here are actually positive and increasing, and these slopes are negative and increasing as we go up the y-axis. So immediately, A and B are out of the equation because the slope is not 0 whenever x is 0. Okay, so the next thing we want to look is where is it infinite? Well, it's going to be infinite when y equals 0 or when we are along the y-axis. And it looks like if you look at all these slope fields right here, or x-axis, sorry, not y-axis. If you look at the x-axis of all these fields, it looks like those slopes are approaching infinity as we're getting close to the x-axis, because you notice the slopes kind of turn into straight lines when we get really close to the x-axis. So that doesn't really help us. So the last trick you can do, once you've eliminated these tests of looking at where the slope is 0 and looking at where it's infinity, then you just plug in numbers. Okay, so for instance, let's keep x as equal to 1 and see what would happen with y. So if x is fixed as 1, the slope is going to vary as 1 over y. So therefore, when y gets bigger, the slope should decrease. And as we see, and it should also be positive. Now that immediately eliminates this one because we see when x is a value similar to 1, the slope is negative and it's actually decreasing. So that doesn't fit. And when we look at this one, around x equals 1, yes, the slope is positive, but it's actually increasing, not decreasing. As you notice, as y goes up, the slopes are getting steeper and steeper and steeper. So that eliminates this one. So therefore, by process of elimination, this one is E. Now, there are other methods you could have eliminated these other choices, and that's kind of up to you on what your strategy is. But notice that process of elimination really is the best way to go about these particular types of problems. So we'll look at some examples of this stuff tomorrow, so just come to class ready with questions.